Good evening, everyone, or whatever time you're watching this. I'm taping this in the evening, so I guess that's the natural thing to say. Mr. Burke here. I'm looking at chapter 4. I am going to look at problems in my math lab, but instead of jumping back and forth between paper and the problems in my math lab, what I actually did was to print some of the problems from my homework, from the homework assignments in my math lab, and I'm going to do an actual sampling of the problems directly on the paper. So that way I can just keep the work on the paper. Since none of these calculations are going to be done directly in StackCrunch, um, I figured this is probably just the more practical way to do this. So let's go to the paper and let's take a look at some of those examples. Do have the notes that we went over in the first video handy, because we will be referring to the properties on those notes so you get a better idea of what those mean. Okay, so, and again, these are directly tied to some homework problems that you're doing. Okay, so let's go ahead and take a look at this. So this is in section 4.1. I think I have this. Yes, I do have this actually in 4.2, but I'll go ahead and refer to this, and not a big deal. So it says, what does A denote? And it says event A naught denotes the complement of event A, meaning that A naught consists of all outcomes in which event A meaning that A naught consists of all outcomes in which event A does. Did that get cut off? Event A does not. I'm gonna say this is probably does not occur. That's the only one that would make sense. And in fact, that's what it is. Now it says here in the beginning, if A denotes some event, what does A not denote? The event that event A does not occur. If the probability of A is 0.009, what's the probability of not A? Okay, so that's the event we're talking about here. We mentioned that these have to add to 1. And it mentions that the probability of not A is equal to 1 minus the probability of A. So we're going to go ahead and use that here to calculate it. So we know the probability of A naught is equal to 1 minus the probability of event A. They tell us that the probability of event A is 0.009. So this is going to be 1 minus 0.009. And that's going to give us 0.991 for the probability. And that's how question 1 is done. Okay, so hopefully that helps clarify from the second page of the notes in the lower right hand corner on the idea of complement and what makes two events complementary. All right. We also use complements in angles. We talk about two angles ending to 90 degrees. Similar idea. In this case, that we're applying it with probability. Second question. A weather forecasting website indicates that there was a 50% chance of rain in a certain region. Based on that report, which of the following is the most reasonable interpretation? Now, you notice here that the kind of answers are already given. And this is why I didn't talk about the meaning of this so much. This would be one of those things that you should kind of get from their reading in the book. It says, there is a 50% probability that it will rain somewhere in the region at some point during the day. It doesn't have to rain 50% of the day. That 50% of the region will get rain, the 50 won't. Okay. Just a 50% probability that at some point of the day, rain will occur. So I don't know if you've I don't know if you're going to watch it this weekend, but we actually have a chance. If you're watching over this weekend, we actually have have a reasonable chance of rain, and thank goodness the heat wave is over. So let's take a look at question 3. Now let's move this down. It says, which of the following values cannot be probabilities? So what this is a question of is a property at the bottom of my notes on page 1. And that's a probability that that's the property that all probabilities have to be between 0 and 1. They can't be greater than 1 and they cannot be less than 0. So what we'd be looking at here is we'd have to convert. If you didn't know what the value of something was, you'd have to convert it to a decimal to check it out. Like 3/5. Well, 3/5, if you divide that, that's going to be 0.6. That should be okay. Now, negative 0.9, remember, it can't be less than 0. That's out. 1.19, that's greater than 1. That's out. 5/3, that's actually going to produce something like 1.67. So that's out. 0, 0, yes, 0 can be a probability. So it can be between 0 and 1, but it can be 0. 0.05, yes, that can be a probability also. 1, that can also be a probability. That means it's like definitely going to happen. 0 means it's absolutely not going to happen. Now, radical 2, if you work that out, radical 2 works out to be about 1.4142. That's my recollection. Don't matter what's after that because we know it's going to be greater than 1. So radical 2 is out. Now, it's asking which one of these I should have done this backwards. It says which of these cannot be probabilities. So which ones did we cross out? We crossed out 1.19. We crossed out negative 0.49. We crossed out 5/3, okay, and then we crossed out radical 2. In fact we boxed 0, so we know that's possible. We boxed 1, so we boxed 0, we boxed 1, we boxed 0.05, and then we also boxed 3/5. So now sometimes they can ask this question two different ways: which could be the probability, which cannot be the probability. So know what you're doing in that regard. I usually just convert everything to decimals if it's not a decimal. Sometimes I can look at the fractions, I can tell they're less than 1, but if you cannot, use a calculator to convert everything to decimals. And I hope you find that to be excellent. Let's take a look now at question 4. It says 10 of the 100 digital videos, let's go and put a number there. 10 of the 100 digital video recorders, DVRs, in an inventory are known to be defective. What is the probability that a randomly selected item is defective? So in this case here, this is one of those events that you're not equally likely to get an effective or not a defective one. But we're going to take the total number of recorders, which is 100, and we're going to take the number that are defective, which is 10. And if you write that as a decimal, that's going to be 0.1, which is the answer they obtained there. But you take the total number of recorders and divide it by the total number of defective ones, since you want the probability that a random selected is going to be defective. So we could say this would be like the probability that you're going to choose a defective recorder is 10 out of 100, because 10 of them are defective, and then there are a total of 100. I just want to say questions because that's what I asked in class. And I have to remember, I'm not in class, so I don't have to ask you if you have any questions. You can ask questions by sending me like an email or a message here as you're watching these, but I do hope that you do find these helpful. Okay. Let's take a look at this. So it says assume that 2,200 births are randomly selected. And then it says only 100, it doesn't say only, but it says 101 of the births are girls. So let's imagine like 101 girls are born and then 2,099 boys are born. It says use subjective judgment to determine if the number of girls are significantly high, significantly low, or neither significantly low nor significantly high. Now, usually if we're going to look to see if something is unusually low or unusually high, or significantly low or significantly high, we would take a look at the probability of that happening being less than 5%. But here they're telling you to exercise subjective judgment. So we're not looking at this objectively. So you have to say to yourself, if 2,000 kids were born, you're usually going to expect about 1,100 to be boys, 1,100 to be girls, because the probability of having a boy or girl is about 50%. It's not exactly 50, but it's about 50%. So this would be like a significantly low number of girls being born, but that is not determined by criteria. What we would usually look at, what will make the event like unusual, like if we're looking at some kind of event that has a probability of less than 5%, which is on the first page of the notes here, but that is not what is being asked in this question. Here they are telling you use subjective judgment. Okay, let's take a look at number 6 then. It says, in a certain instant lottery game, the chances of a win are stated as 4 in 19. I wish I'd play that game. Express the indicated degree of likelihood as a probability value between 0 and 1. So when we say 4 in 19, that's going to be 4 divided by 19. And if you divide that out, that's going to be 0.211. And that's how that's going to work. Okay. Number 7. Express the indicated degree of likelihood as a probability value between 0 and 1. When using a computer to randomly generate the last digit of a phone number to be called for a survey, there is a 1 chance in 10 that the last digit will be 0. Okay, so that means that if you're going to pick between 10 digits, there's only 1 0. So that's going to be 1 out of 10. So that's going to be 0.1, which is what we have here. All right, let's take a look at, I'll do 8 and then I'll go on to, I think the next problem is it more, yeah, it's actually more of this. So I'll do 8, I'll skip 9. It says it is impossible to get 7 kings when selecting cards from a shuffle deck. So we talk about a shuffle deck, we're talking about one deck of cards. So we're not talking like when you go to Vegas and there's like, 10 or 15 decks put together when you're playing like at the craps table or anything like that, or not craps, when you're playing at the 21, table with a poker table like this. Okay. Actually, poker would probably be played with a single deck. I don't think it'd be multiple, but I don't know. I'm not a big gambler. Express the indicated degree of likelihood as a probability value between 0 and 1. Hopefully most people know that the most kings that there are in a deck of cards are 4. So there's going to be 4 kings. So if you're playing with one deck of cards, the probability of getting 7 kings, that's impossible because there's only 4 to pick from. So you just write the probability as 0, and that's it. Okay. So that's going to be that. Let's go and take a look at another problem here. I just want to kind of see where I'm up ahead. Okay. So this is going to be question number 10. It says, refer to the sample data for pre-employment drug screening shown below. If one of the subjects is randomly selected, what is the probability that the test result is a false positive? Who would suffer from a false positive result? And then, like, why? Okay, we'll talk about that. It says, what's the probability of a false positive test result? So the first thing we need to determine, I'm going to come back to this chart a little later, is how many total people are there. So we need, if we're going to figure out the total, what we need to do is we need to add all 4 of these numbers. This is going to be 46 plus 20, 66 plus 8, 74 plus 30, that'll be 104. Okay, so we have 104 total people. They might have even put that down somewhere. I would miss something like that if they did. Now they want the probability of a false positive. So first off, what we want to do is we want to find the column with the people who test positive. So the people who test positive are these people right here. Now, if a person is not a drug user, but they test positive, this is the category that falls under false positive. So of the 104 people that are drug tested, of the 104 people, 20 of them get a false positive result, at least in this particular study that they conducted. How they did that, I don't know, but that is what they share. So this is 20 out of 104. And because we don't care about the people that, they're using drugs, but we're talking about the false positives. So this is going to equal 0.192. And that's going to be the percentage of people, the proportion of people that are false positive. So, and then they ask, who would suffer from a false positive test result? Why? Instead, the person tested would suffer because he or she would be suspected of using drugs, when in reality, he or she does not use drugs. So this has got cut off. He or she does not use drugs. So sure, because if you test positive, that can impact employment with certain companies. Even like marijuana, for example, may be illegal, but companies can still insist on hiring people that don't use marijuana because they're afraid of them, coming to a job under the influence. So companies, even in California, do have that right, even if marijuana is legal in the state. So, and definitely in New York, like if you're a teacher and you ever smoke marijuana, they won't even hire you. I know in California they are more lenient on teachers who have prior like marijuana convictions, but not in New York. They will have none of it. All right, let's go ahead and take a look. I'm gonna take a look at let's take a look at 11. We'll skip 12. If you know, yeah, let's take a look at 12 actually. So it says here, in a genetics experiment of peas, one sample of offspring contains 450 green peas and 126 yellow peas. Based on those results, estimate the probability of getting an offspring pea that is green. Is this result reasonably close to the value of 3/4? Okay. Now, um, so just the answers you're going to get in your homework are going to be different because the questions are going to be slightly different. Okay. So I'm going to show you how we determine if something is reasonably close or not reasonably close. So what we want to do in this question is because it wants the probability of getting an offspring P that is green based on what we have here. So how many total do we have altogether? It's 450 plus 126. So the total we're going to have is 576. And then the part of the portion that is green is going to be 450. And if I take 450 and I divide it by 576, that's going to give me the answer 0.781. All right. Now they ask a question. Is that probability reasonably close to 3/4? Okay. What is reasonably close? That is a less than 5% difference. Now we're going to take a look at what reasonably close means a little later, but when we talk about reasonably close, we're talking less than a 5% difference. If, for example, we were told it's 75% and we got a probability of like 85%, that's not reasonably close. That's a bit off. So as a general guideline, we look at that being a less than 5% difference. And because 3/4, we look at this as a decimal, is 0.75, and we obtain a probability from the data here being 0.78, we can say that that's reasonably close. Now, not all the questions you do in your homework will be reasonably close. Some of you will have some that are not. Okay, so be sure to look for assistance on this from the program if you want to get that. Okay, this will be the last question I provide assistance with. It says, to the right are the outcomes that are possible when a couple has 3 children. If you read Triola's book, he talks about a simple event having 3 kids, which, as I always say, is how you know Triola was a man. Only a man could say call the event of having 3 children something simple. I think if we already have 1 kid itself, he may see otherwise. I mean, cute with the language. I know what he means by simple events statistically, but in the real world, having kids ain't simple. I mean, I've not done it myself, of course. I am a male, but all women tell me otherwise. So I'm going to take the word for it and leave it at that. So it shows what the possible outcomes if you have 3 kids. You can have 3 boys, you can have 3 girls, like 2 boys and a girl. You can have like here's 2 girls and a boy. Here's another like a boy, 2 boys and a girl, 2 girls and a boy, 2 girls and a boy, 3 girls, like this. And it says, find the probability that when a couple has 3 children, there is exactly 1 boy. Okay. So in the case when they have 3 children, the probability of exactly 1 boy. Well, first off, each of these represents an outcome. So we're looking at the probability of 1 boy. We'll write it like this. If you have 3 kids, there are 8 possible outcomes to this. So let's put that there. We want to see how many outcomes involve having just 1 boy. So that's 3 boys. That doesn't work. 2 boys. 2 boys. Here's 1 boy. Girl, boy, boy. Doesn't work. Girl, boy, girl. That works. Girl, girl, boy. That works. Girl, girl, girl. So there are 3 out of 8 events where you can have exactly 1 boy. Doesn't matter if the boys hit first, second, or third, but there are 3 possible events out of 8, which is how we get the answer to question 14. All right. And on that note, we're going to go ahead to, I have a few questions back here too. So let me see which ones I'd like to share. 15 is pretty similar to what I went over. Let's see. Yeah, I think let me go through this one here. I'm not going to go through 15. It says use the given probability value to determine whether a sample result could easily occur by chance, then form a conclusion. Okay. So it says here, a study addressed the issue of whether pregnant women can correctly predict the gender of their baby. There are a lot of old wives' tales. They say like if you gain the weight in front of your tummy, that's a boy. If you gain the weight of the hips, that's a girl. There's all kinds of tales over here back east. I don't hear much here, but Becky's for sure hit them. Among 104 pregnant women, 57 correctly predicted the gender of their baby. If pregnant women have no such ability, if pregnant women have no such ability, there is a 0.327% probability of getting such sample results by chance. What would you conclude? So it says here, if pregnant women have no such ability, that this is the probability they're going to get it by, they're going to get this by chance. So they're going to get this right by chance. So it says the probability, okay, so what we need to figure out is we need to take 57 and divide this by 104. And if you take 57 and divide that by 104, that's going to equal 0.5 exactly. It means half the time they're right, half the time they're wrong. And we're going to say here, the probability shows that the sample result could have easily occurred by chance. It appears that there is not sufficient evidence to conclude that pregnant women could correctly predict the gender of their baby. Yeah, so like half the time they're right, half the time they're wrong. So, that's what they're going after. It's kind of an interpretive type question. So, we're looking. So, just want to put that out there. You can read up on this a little bit too if you want. But depending on the data here, this could go either way. So be careful and read the question carefully. This is usually not the kind of question I'm going to put on the test, not to later on, because I don't want to talk about like doing the interpretations on this too much, but I do want you to begin to get a little familiar with working with these. Now let's go ahead and go to 4.2. All right. Looking at, I have the question circles. I went through these already. It says, when randomly selecting an adult, A denotes the event of selecting someone with blue eyes. So what does piece of A represent and then piece of A not represent? So piece of A will represent the probability of selecting an adult with, sorry. What does piece of A represent? That's a probability of selecting someone with blue eyes. And that's what they just kind of said. And then they ask, what does P of A not represent? That's a probability of selecting an adult who does not have blue eyes. I think within the US population, I think it's about 11% of people have blue eyes. I found that proportion to be significantly higher on the East Coast than on the West Coast. I know when I fly back to Buffalo to go see my film at Christmas time, all these people are like from Buffalo. You can tell they've moved across the country. And I would say a significantly higher proportion of the people that are like flying back to Buffalo have blue eyes. And that comes mainly from the German Polish populations that populated Buffalo back at the late 1800s, early 1900s. So definitely a higher concentration of like more Northern European who are usually have a higher proportion of blue eyes. So anyway, that's the interpretation for number 1. Let's go and take a look at number 2. It says there are 15,958,866 adults in a region. If a polling organization randomly selects 1,235 adults without replacement, are their selections independent or dependent? Now, it says without replacement. Okay, so 2 concepts here. Are the selections independent or dependent? If these selections are dependent, can they be treated as independent? So, going back to the notes we discussed for page 2, I mentioned that if there's no replacement, that they are not independent. Therefore, they are, and I should have used this word, they are dependent. So as a matter of technicality, these selections are going to be dependent because the selection is done without replacement. So that comes directly from notes. However, there's something at the bottom of the page also I noted. And here is this 5% guideline. If the sample size is no more than 5% of the size of the population, you can treat the dependent selections as independent. So if we were to, let's say, take 1, 2, 3, 5, and we divide this by 15 million, and you can do this. I'm not going to because it's such a ridiculously large number. But if you were to take 1255 and divide it by, as long as this is less than 0.05, what we're saying is we can go ahead and treat them as independent. So the answer to this is yes, because the sample size, which is 1235, is less than 5% of the entire population, for sure. So like 0.0005. It's really, really small. So we can treat them as independent. And that's what I'm talking about in this principle down here. Okay. So let's take a look at number 3 then. A research center poll showed that 79% of people believe that it is morally wrong to not report all income on tax returns. Okay. So it is morally wrong. I wonder when they did that poll. I'm going to say that number's a little less today. But don't worry, the IRS is hiring a lot of people to do audits and everything. What is the probability that someone does not have this belief? So if this is the probability they do, like you're going to find it morally wrong, and they're kind of assuming you're not going to find it morally wrong, which kind of makes sense. We're assuming that there are no agnostics on this, like they're not sure. We're assuming you either find it wrong or you don't. So let's say if we'll say the probability that it is ethically wrong is 0.79, then we want the probability that it is not ethically wrong. That's going to equal 1 minus 0.79. That'll be 0.21. And that's the answer we have there. So what they're going after is this whole idea of the application of the complementary probability. I have at the bottom of the notes on page 2. Let's take a look at number 4. In a computer, instant messaging. Oh, sorry, not number 4. I wasn't going to go over that one. I want to go through a few of these with tables because we're going to take a look at the addition rule with a table, which is a little different than other problems that you probably would consider. It says, use the data in the following table, which lists the drive-through order accuracy of popular fast food chains. Assume that orders are randomly selected from those included in this table. If one order is selected, so we're talking about one order, so this is one event. Okay, find the probability of getting good food that is not from restaurant A. So we want to get not good food. Getting food that is not from restaurant A. So there are a couple ways you could do this. First thing we need to do is we need to add all these numbers together because we need to figure out a total. I'm looking for my phone here. Okay. I like to use my phone for the lesson here because it shows up so nicely. Of course, remember you will not be able to use a phone for this. So why is it like dark? It's maybe because of the light coming. Yeah, the light coming down. There we go. That should probably work. Okay. So yeah, people will be able to see that. So that's gonna be 339 plus 276 plus 237 plus 130 plus 40 plus 60 plus 31 plus 18. So my total is going to be 1131 in this question. So I'm doing a probability. That's going to be 1131. Now it says if one order is selected, find the probability of getting food that is not from restaurant A. So probably what I'd like to do is just figure out, I can either add these numbers, okay? And what I'll probably do is I'll just end up, so I have the total here. I'll just take away these two numbers from the 1131 I just came up with, because if I take these two numbers away, that'll give me the total of these numbers. Because if it's not from restaurant A, then I just want the numbers, the probably getting food from B, C, and D. So I'm just going to take these two numbers away to get the sum of these. Someone will tell you, like, just add, I can add these, but I'm just going to take these two away so I come up with this total. So it's going to be 1131, which is sum of all these, minus 339 equals, and then minus 40. So if I added all 6 of these numbers up, the sum I'm going to get is going to be 752. And let's take that now and divide that by 1151. And we get 0.65. Well, 6, hold on. Let me see something here. Let me make sure that my answer is just a little different from this one. So let me check my math on this again. So 339 plus 276 plus 237 plus 130, okay, plus 40 plus 60 plus 31 plus 18. Oh, yeah, I got 1131. Okay. So let me, okay, so then let me try to, let me make this, let me just add these up and make sure I did that correctly. So let's say 276 plus 60 plus 237 plus 31 plus 130 plus 18. So 752, that's what I got. Let me divide that by 1131. Ah, okay. So I must have did something wrong on my division last time then. So that's 0.6648. So I rounded up to 0.665. And that's how I get that result there. All right. So let me do let me see here. I want to, yeah, let me do I'm actually gonna do question 6 on this one. This is more the kind of question I'm looking to. If one order is selected, find the probability of getting an order from restaurant A or an order that is accurate. Okay. So let's take a look at how this is done. So here's that word or. And usually when we see that, this is going to be an application of the addition rule. This rule right here. So we're going to look at applying that rule in this question. But this is going to be in a table now. So let's see how that works. So we want in the probability of getting an order from restaurant A. So I'm going to circle that there. Or an order that is accurate. So I'm going to circle this here. All right. So what I need to do with this again is I need to get a total on this first. Okay. So that's going to be 331 plus 266 plus 245 plus 139 plus 33 plus 52 plus 38 plus 10. So, so the total on this one's going to be 1114. So we're going to be using that total number of our probabilities. So I want the probability of getting an order a restaurant A or an order that's accurate. So let me I hate that this is restaurant A and that this is accurate because I'd like to use I just what I'm going to say is the probability of R. That's going to be the probability of getting an order from that particular restaurant. And then I'm going to say the probability that the order is accurate. Okay, so I'm going to have this. So the rule I'm going to write is, what's the probability of getting an order from restaurant A or getting an order that is accurate? Okay, well, that's going to equal the probability of getting an order from restaurant A plus the probability of getting an order that is accurate minus the probability of getting an order from restaurant A, or sorry, from restaurant A and it's accurate. So let's take a look at what happens with this. Okay. So in each of these probabilities, one thing that is going to happen, that the total is going to be 1114. So write that down, get it out of the way. So what we want to do is we want to find the number of people that get an order from restaurant A. And that's going to be determined by this column here. So this going to be 331 plus 33, and that's going to be 364. That's the first one. Now we want the probability that they're going to get an accurate order. So that's going to be the sum of these four numbers here. So that is going to be 331 plus 266 plus 245 plus 139. And that's going to equal 981. Now, if you look at these, you kind of add these together and say, well, this adds up to greater than 1. It's the part we're going to subtract. Now, what are we going to subtract? The number of people who both get an order at restaurant A and the order is accurate. And where that occurs is right here, because you'll notice that in the data, we've counted 331 across and we've counted 331 downwards, meaning that we've counted 331 twice. So we need to take that 331 away from the calculation. And that because that's an event in which not only are you getting an accurate order, but you're getting it from restaurant A also. So in order to come up with an answer to this, what we're going to do is we're just going to figure out the numerator to this. So this is going to be 364 plus 981 minus 331. And that's going to leave me with 1014. So this is going to be 1014 divided by 1114. And if I take this result and divide it by 1114, that's going to equal 0.910, which is what we have here. Now it says here, are the events of selecting an order from restaurant A and selecting an accurate order disjoint events? Okay, if you have, unless this is 0 right here, the probability of A and B, unless this is 0, these are not disjoint events. These events are not mutually exclusive. So we say the events are not disjoint because it is possible to receive an accurate order from restaurant A. And these are the number of people who receive an accurate order from restaurant A. So that's what they're talking about there. So feel free to watch that a few times to kind of make that clear for yourself. But I hope that, that example kind of clarifies things. Okay. And if this video is long, I apologize, but I did want to try to knock this out in one video because just it's more time to make more videos than this fewer. So, all right, let's take a look at number 7 now. I don't know if I want to do that one at this point. I feel like I've gone through. See, yeah, I'm gonna let you guys try these other ones here. Because I don't want to do all these for you. I feel like you should try some of these. Let's go ahead and try number 9 then. Use the following results from a test for marijuana, which was provided by a certain drug testing company. Though this is an example where they're giving you the data without the table. So we're gonna have to kind of build this table. We'll take a look at that in a minute. Among 150 subjects with positive test results, there are 20 false positive results. Among 155 negative results, there are 5 false negative results. Complete parts A through C. And they say, hint, construct a table. So I want to refer back to a previous question that provides a little guidance about constructing a table for this. Because I know I tried constructing a table on this once and I was not real successful. Just because I kept making mistakes in terms of how the table should be organized because there's a few ways to think about it. So take a look at this one. You have the positive test result, you have a negative test result, the subject uses drugs, and the subject doesn't use drugs. So to use that structure here, okay, got a call from Folsom, California, which, that I don't trust. Okay, so and we'll kind of divvy it up like this. And they also give us totals on things here. Okay, so what do they give us total on? So in the question, hold on. Oh, I think I kind of, there we go. Let's take a look at this here. So here's the question. It says among 150 subjects with positive test results. So this is 150 down here. This represents a total. That's a total number positive. It says 20 of them are false positive. So how many of these are false positive? Because they're not a drug user, that's 20. So if there's a total of 150 and 20 of them are false positive, that means that 130 must be drug users because these two numbers have to add 150. Okay. Another one here. Among 155 negative, really 150 positive results, 155 negative. My God, are they in like a Eureka or something? Among 155 negative results, there are 5 false negative results. So here now, what do they mean by false negative? Okay, that they use drugs. So the 5 is going to go up here because they got a negative test result, but because it's false negative, that means they use drugs. So that means 5 plus 150 equals 155 because these two numbers here have to add to 155. So now we have the values in our table and we have the table constructed. So with that in mind, let's go ahead and let's take a look at the questions and see what we can find. Okay. Yeah, I'll try to get all this in here. All right. So how many subjects were included in the study? Well, you have 150 plus 155, so that's 305. So that's done. How many subjects did not use marijuana? Okay, so we have those that are not drug users. So we have 120 plus 150, that's gonna be 170. And then it says total 170 did not use marijuana. What's the probability that a randomly selected subject did not use marijuana? Okay, so this is the number of people that did not use marijuana. This is the total number of people. So that's going to be 170 over 305. And that total, if you divide it out, it's going to be equal to 0.557. So yeah, this is one of those problems I definitely wanted to go over because I wanted to show you how to put this together, particularly when you have that false negative, that's going to be a person who is, they got a negative test, but is drug user. So this kind of problem is really tricky. So I wanted to be sure I gave you an opportunity to see how I constructed the table for doing question 9. And I hope people find that helpful for completing the homework. All right, just a couple more questions to go. And this is going to apply the multiplication rule now. There's not a whole lot of work on this because even though students are required to study probability, this is just meant to kind of give you a sense of how probability works. Most of the probability calculations are now done in StatCrunch, so there's not a whole lot of work that we do with probability, but we're still going to spend some time with it just to help everyone build a sense. All right, the principle of redundancy is used when system reliability is improved through the redundant or backup components. Assume that a student's alarm clock has a 6.4% daily failure rate. Boy, you can tell this is an old question. Which student has an alarm clock these days? Everyone uses a cell phone. I'm thinking yes. Okay. No, Triola needs to update his work. I'm just saying. Complete parts E through D below. It says, what's the probability that a student's alarm clock will not work on the morning of an important final exam? So they want this at 3 decimal places. So if we know it is 6.4%, then we can move the decimal point 2 places over to get 0.064 as a decimal. Okay. Now it says then, if the student has 2 such alarm clocks, what is the probability that they both fail on the morning of an important final exam? So this is, in other words, the professor is trying to tell you, like, if your alarm clock didn't go off, they're not going to believe you, So what's the probability that the first one doesn't go off and the second one doesn't go off? Now, are these 2 alarm clocks going to be independent of each other? Yeah, just because alarm clock doesn't go off the first time shouldn't have any effect on the second alarm clock. So this is going to be 0.064 times 0.064. And that's what's going to give you the probability of 0.00410. You can probably write this as the probability of failure and failure. Like the first one fails and the second one fails. So that's going to equal the probability the first one fails times the probability that the second one fails. I would put the condition about given the first one fails, but what happens with this one should not impact the probability of this. These would be independent. Okay. What is the probability of not being awakened if the subject uses 3 independent alarm clocks? Oh, see, okay, so they actually say that these are independent alarm clocks, because that needs to be said. So if it's 3, then it's going to be like 0.064 times 0.064 times 0.064, which is going to be 0.064 to the third. And that's what's going to give you 0.00026. Now, again, remember, you're going to have slightly different numbers, but the question is going to look pretty similar, but this is how it's done. Up here, you could write this as 0.064 to the second, but I felt it kind of complemented this procedure nicely, okay? And it goes, do the second and third alarm clocks result in greatly improved reliability? And it says one that yes, because the total malfunction would not be impossible, but it would be unlikely, okay? So what I mean by this, an event that has a probability of 0.064%, like 6.4%, this is not 0.064%, it's 0.064. It has a percent at 6.4. So if that were true, 6.4, something that has the probability of 6.4% is not considered unlikely. But when you start going to probabilities that are less than 1%, then it becomes unlikely because these probabilities are less than 5%. So yes, malfunction would not be impossible, but it would be unlikely. By unlikely, they mean it's less than 5%. That's what they mean by unlikely. One is not unlikely. One is not less than 5%, but the probability of 2 or 3 failing is less than 5%. That's what they're going after in question 10. So be aware of that because and I think that's probably going to be the same answer, but we'll see. Let's take a look at number 11. Last question we're going to do here. Says among 6,628 cases of heart pacemaker malfunctions, 377 were found to be caused by a firmware, which is software programmed into the device. Ooh, man, that's not one thing you want to be messing up the software on. If the firmware is tested in 3 different pacemakers randomly selected from this batch of 6,628, and the entire batch is accepted. Oh, so hang on. So let's read this again. If the firmware is tested in 3 different pacemakers randomly selected from this batch of 6,628, and the entire batch is selected if there are no failures, what's a really run-on sentence? What is the probability that the firmware in the entire batch will be accepted? Okay. So is this process likely to result in the entire batch being accepted? Okay. So first off, when this is chosen, we're picking 3 out of 6,628. Okay, so by doing so, the sample size is less than 5% of the population. So in terms of probability, we're going to categorize that these are going to be independent. So if I want the probability of none, if I want the probability of none of these being defective, that's going to be the probability that it's going to be the probability the first one doesn't work. The first one is not defective, so it's effective, times the probability the second one is effective, times the probability the third one is effective. All right, so we want to make sure that all of these work. Now, according to this here, it says that 377 out of 6,628 have malfunctions. So if we want the probability that they're going to be effective, if you took 377 and divided by 6,628, that's the probability, that would give you the probability they're going to be defective. If you want the probability that they're going to be effective, we need to take 6,000, so watch how this is done. This would be 6,628 minus 377, because either they're going to be effective or they're not. So this is going to be 6,628 minus 377. Ooh, hold on. That was wrong. 6,628 minus 377. So that's going to be, of those 6,628, we can expect 6,251 to be working. All right. And that'll be the number of effective ones. So this is going to be 6,251 over 6,628. And because we're treating these as independents, this would be the same probability, like times 6,251 divided by 6,628 times 6,251 divided by 6,628. So we can write this as this to the third, because we'll be multiplying the same number 3 times. And that being the case, we say the probability that's going to be 0.839. And as a result, we say the procedure is likely to result in the entire batch being accepted, because the chance of it is like almost 84%. So that's pretty likely. Okay, so that is a sample of the homework problems from section 4.2. So that's going to cover chapter 4, and I hope that you found this helpful. Thank you.